Hello everyone and welcome to Campus 101 exam series. My name is Dr. Piro. We're looking at physics. Today we're going to be looking at a very dangerous topic. This topic is the topic of radioactivity. Before we start, radioactivity is very dangerous. Radiations are dangerous. I'm cancelling the topic because it is dangerous. Now, this question came out 2 years ago in your exams. Why is radioactivity so dangerous? 1, because it causes cancer. 2, because it is toxic to the population, to everybody. So radioactivity causes cancer and it's toxic. It's toxic. So what is radioactivity and why is it so bad? But before we look at why it's so bad, we need to go through some terms. We need to go through the physics and then we'll see the dangers behind it. Meanwhile, for all the female students watching today, you have to be proud of yourself because Madam Maria Curie, one of the most brilliant minds in science to ever live, was the woman who studied radioactivity, and she did a great job. And because of her today, we can enjoy radioactive power, we can enjoy nuclear energy and all that. So cheers, kudos to all the females in the house and to Maria Curie. Now let's look at definition of terms. Before we go into those terms, I want us to look at the structure of an atom. Traditionally, classically, this is what we say the atom looks like. The atom is made up of, it is usually defined classically as the smallest indivisible unit of an element. Now we know we can divide an atom, but we're just going to use that definition for this class. In the center of the atom is the nucleus, and the nucleus, we know that the nucleus is positively charged because the nucleus is made up of protons. Let me make my protons red. And still in the nucleus of the atom, there are also what? Neutrons. Neutrons, exactly. Now, surrounding or circulating this nucleus is a small part of the atom that we call the electrons. Let me represent it blue as E there. All right. So classically, this is what we see when we talk about an atom. An atom is made up of a centrally placed positively charged nucleus, and circulating us, orbiting this nucleus are electrons, and then electrons here are negatively charged. So now we know that the proton is in the nucleus. We also know that within the nucleus are uncharged particles. These ones are called neutrons. They weigh almost similar to the protons, but they are not charged. I've represented my protons with red and my neutrons with purple. Now we've also looked at electrons, and we say electrons are negatively charged. So positively charged, negatively charged, zero charge. If you are with me so far, then you know the basic structure of an atom. Now let's move it a little bit further. Next thing we're going to be looking at are another important component of this discussion, and we're going to call this, when we look at the mass of the nucleus, the mass of the protons and the neutrons, what that gives us, the mass of the protons and the neutrons, we're going to call it the nucleon number. The nucleon number. No, it's spelled as nucleon. Yep. So the nucleon number is the number of protons and neutrons in the atom. So that's the nucleon number. I need you to know this because it is important in your exam. It comes as frequently asked. All right. So the next thing I want us to look at is a helium atom. So what is a helium atom? Yes, my chemistry students will know that a helium atom has it has a mass number of 4 and an atomic number of 2. What this means is that it has 2 protons, 2 neutrons, and 2 electrons. I'll tell you why I want us to look at the helium atom very soon, but just know this helium atom. Alright, so now let's go back to radioactivity now that we've gotten the fundamentals in place. Alright, radioactivity is a phenomenon that occurs because as the size of atoms increase, as the atomic number increases, we see that there is an increase in the instability of the atom. I'm talking about atoms with very large atomic numbers here, greater than 100, mass numbers of close to 200. All right, we're looking at atoms like uranium that have a very large atomic number. An atomic number is the number of protons in the atom. All right. So we see that uranium is the largest. Uranium is the largest natural, or call it natural, keyword natural element that has a stable nucleus, and even this nucleus is not stable. What I mean is that as we begin to increase the number of protons and neutrons within the nucleus of this atom, we see that the nucleus becomes unstable such that it begins to disintegrate. And how does it disintegrate? It begins to give off some of its subatomic particles. So it begins to give off some protons and neutrons and some electrons. And as it does this, not only does it give all this, it also releases energy in the form of radiation. And this energy in the form of radiation particularly comes through what we call gamma rays. So I've introduced some new terms now. These new terms I've introduced include what? Instability of the nucleus. I've also told you about gamma rays. Gamma rays are not charged. They are very strong and they are very dangerous. Gamma rays can pass through the human skin. Gamma rays can pass through walls. The only thing that can stop gamma rays is a block of concrete or lead. And lead is one of the densest metals we have on Earth. So either a block of concrete or a coat of lead, a dense coat of lead is what can stop gamma radiation. All right. Other forms in which radiation is given off includes beta rays. Now, beta rays, we know beta rays to be electrons. Why do we know? Because they're electrons? Because they're negatively charged. I told you gamma rays are not charged. Electrons are negatively charged. And then another form in which radiation can be given off is alpha particles. What are alpha particles? Alpha particles have a mass number of 4 and they have an atomic number of 2. So we know that alpha rays are similar. They are very similar to the helium atom. And that's why I wanted us to look at helium atom at the beginning of this discussion, because there are 3 primary ways of radiation. Radiation can be alpha rays, and alpha rays we said are helium atoms. It can be beta rays, which are essentially electrons, and it can be gamma rays. And gamma rays, I told you, are uncharged. They are just rays of energy. All right. So I'm going to represent it here with such of a lightning bolt. All right. So these are the 3 chief forms in which radioactivity or radiation or radioactive energy, right, exists in. I need you to be very clear about this because it is very important and very fundamental to your knowledge and understanding of radioactivity. Now, the next thing I want us to look at is it's a step more complicated than what I was looking at so far. The first thing I'm going to say now in this next step is nuclear fission. Yeah. Nuclear fission. What is nuclear fission? The word fission, I want you to know that it means to scatter, to break away. So nuclear fission is actually the energy required, and I'm going to represent energy as delta E here. The energy required to split is the energy required to split the nucleus of an atom. To split the nucleus of an atom. When we split the nucleus of an atom, the energy that we need to split the nucleus of an atom is referred to as nuclear fission. And when nuclear fission happens, what happens is that there is release of some subatomic particles, and the ones we're talking about particularly here are neutrons. Remember, neutrons have no charge and they have a mass number of 1, and not just one atomic unit. 1 atomic mass unit. Alright? So when we split the neutrons when we split the nucleus with release of neutrons, the energy required is referred to as what? Nuclear fission. Now, the next related term, which is confusing, I want us to look at is nuclear fusion. Right? So fusion. This is different from fission. Here is fusion. The word is U. This is what is the energy again? Delta E required to merge 2 smaller nuclei to make 1 bigger nucleus. is the energy required to fuse two smaller nuclei to give one larger nucleus. I hope you can see this well. Alright, so that is nuclear fission. The energy required to merge two smaller nuclei to make a big nucleus, a bigger nucleus, is referred to as nuclear fusion. So it seems our discussion so far have just been about definition of terms, but we need to get this clear because they are so frequent in your exams. All right, so the next term we're going to be looking at again, which is very critical to our discussion of radioactivity, all thanks to Maria Curie and her team, is we're going to be looking at the use. We're going to be looking at the use of radioactivity. So what are the uses of radioactivity? Since radioactivity is so important, what are its uses? Turns out that even though it is so dangerous, causing cancer and all that, in fact, I want to tell you that the atomic bomb that was dropped was based on the principle of radioactivity that was dropped in the Second World War in the city of Hiroshima and Nagasaki in Japan. Hiroshima was based on radioactivity. All right, the nucleus of an atom, uranium, was split. The energy was so massive, it killed a lot of people, right? So that's why it's dangerous. But even though it's that dangerous, we use radioactivity in medicine. We use it in the treatment of cancer. So when we put alpha rays on tumor cells, they tend to die. So we use in the treatment of cancer / tumors. All right. We also use radioactivity to power for electrical power. So you've heard of nuclear power, a non-renewable source of energy. So to power submarines and even to produce electricity. All right. So the last thing is used in the generation of electricity. So these are 3 uses of radioactive energy or nuclear energy. So with these uses, all right, I want us to look at 2 other definitions. All right, 2 other definitions. I know this video has been packed with definitions, but it's important because these are the frequently asked questions in your exam. What we're going to look at now is mass defect. Mass defect. What is mass defect? Mass defect is the difference between the mass of an atom and the mass of the nucleon. Please tell me you remember what the nucleon is. We said the nucleon is the number of protons and neutrons, right? Neutrons, all right? So the difference between the mass of the atom and the mass of the nucleus is regarded as the mass defect. And the mass defect, the unit for mass defect is atomic mass unit. Please remember mass defect in your exam. The next one I'm going to tell us to look at before we look at one calculation is binding energy. Binding energy. Binding energy. No, this is not the energy to cast and bind things. This is not the energy to cast and bind things. This instead is the work done. All right. So binding energy is the work done in separating the nucleus of an atom. Separating the nucleus of an atom. So if we have the nucleus of an atom here, made up of neutrons and protons, all right, when we separate the nucleus of this atom from its electron, when we separate the nucleus of this atom from the atom, the energy that is required to carry out this process is regarded as what? The binding energy. All right. So with this, I think I've looked at a lot of definitions today. And how does radioactivity occur? So we're going to look at a question from your exam, and this will be the last thing we're going to be looking at in our discussion today. So the question was like this: an atom, radon has a mass number of 222, but we were not given the atomic number. Now, radon is unstable and dissociates to give polonium. Polonium has a mass number of 218 and an atomic number of 84. And then something was given up. A helium atom was given up, and then this was given up alongside its energy. All right. And the question was for us to calculate Q. What is Q? What is Q and what is P? Alright, so this was the question given in your exam. Now, on the principle of radioactivity, I told you that radioactive wave can either be alpha, beta, or gamma rays. And I told you gamma rays are essentially energy. I told us also that beta rays are electrons and alpha rays are helium atoms with a mass number of 4 and an atomic number of 2. Now, let's add these together. Let us add these together and see if we can find the difference. This atom radon is integrated into polonium. If we see 222 minus 218, what's that difference? 4. And so we know that Q of helium here is equals to 4 and is in keeping with alpha particles of radioactivity. So we know that Q is equals to 4. The next thing we can find out from here is that we know that there is conservation of mass from the basic laws of physics, laws of thermodynamics. Energy is neither created nor destroyed, and matter cannot be created nor destroyed too. Now we have P here and we have 84 here and we have 2. So we know if we add the atomic number between these and these, we can get the value for P. Alright, so when we say 2 plus 84 will give us P. Alright, so if we say 2 plus 84 give us what? Exactly 86. So the mass number of radon here becomes 86. So the summary of this question that we've done so far is that radon has 222 and P is 86. And then we know also that helium has 4 and 2. And that's, so Q equals to 4 and then P equals to 86, and that sums up the answer. And questions can come subsequently like this, but the moment we know the principle of atomic number and mass number, we can easily find our way through questions on radioactivity. Keep this in mind. Always keep this in mind. The rays, the radioactive rays. Alright, so in summary, to quickly summarize what we've discussed so far, we said Maria Curie did a great job in introducing us to radioactivity and its uses. We said radioactivity is dangerous, causing cancer, and it's toxic. We said protons are positively charged, neutrons are positively charged. Both of them live in the nucleus of an atom. Electrons are negatively charged. They stay in the orbit and they circulate, or they orbit around the nucleus. We said the nuclear number is the number of protons and neutrons in an atom. We looked at radioactive particles. We said alpha rays equivalent to helium atom, beta rays equivalent to electrons, gamma rays, which are essentially bolts of energy. We looked at nuclear fission as the energy required to break or scatter the nucleus of an atom. We looked at nuclear fusion, the energy required to merge two smaller nuclei to make a bigger nucleus. We also looked at the uses of radioactivity in the treatment of cancer and tumor cells to power submarines and generation of electricity. We also looked at mass defect as the difference between the mass of an atom and the nucleon of that atom, and the unit is an atomic mass unit. We also look at binding energy as the work required to split the nucleus of an atom. Finally, we look at calculation based on radioactive rays, and we look at how by finding the mass number and the atomic number we can look for P and Q in different questions. Thank you very much and see you in the next video.